So, welcome back, everybody. Yesterday, we did a little bit of free fall acceleration stuff, and I want to stress the heck out of this. All this calculation that we were doing yesterday, when we see g show up in this calculation, like it does, because we have acceleration is gravity times the radius of Earth squared, plus this other stuff, this value you need to be very, 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 very mindful of. The problems that we looked at yesterday was free fall around which planet? Earth. So when we see this g value, it is based on values and calculations that we get for which planet? Earth. Would this equation work for Mars? Not directly. The equation itself would, but would g be different? G would be different. I thought you said no, I'm sorry. I gave you I don't know, a glary look. Somebody's phone's buzzing. Where is it? It's one of these two. Is that true? This one. Whoever's this phone is, Mama's calling. Cool. If you need to step out and take it, you can. Cool. All right. So, I think I'm recording, right? Did I do an intro? Bet. Skibbity what? Riz is the answer. All right. So, we're going to talk about the gravitational field today. Now, we don't have to look at this, but physics has really developed crazy amounts like the last 150 years. So, roughly 500 years ago, around then, is when Isaac came up. Newton, right? It's like we're on first name basis. He's my BFF. That felt really awkward, and I love it. Okay, Newton came around in 1660s and made some big ideas, and people kept building on it, right? So he developed calculus, and other bigger names, maybe in the name of calculus, started developing the mathematics. The physics kind of went on its own. And then all of a sudden, in the 1800s, people started playing around with this idea of electricity. And one of the fundamental forces in our universe, we have gravity, that's one. Electromagnetism is another big one. Turns out, if you haven't talked about it a bunch in physical science, electricity and magnetism are like the same thing. They're just different manifestations of something that happens in our universe. So as we're looking at this, Michael Faraday, which if you guys have ever seen spy stuff, if I have my phone and I think if I'm a spy, let's just pretend, or you're a spy, that works just as well, and you're in a foreign country and you're doing spy stuff, your phone could betray you. Do you guys agree with that? Because maybe the government thinks I'm a spy that I'm spying on, right? And what could they do with my phone? So they could probably turn on my camera, turn on my microphone and all that stuff, right? So somebody might think, oh yeah, I'm good, I'll just turn my phone off. Is that really going to do the trick, you think? No, because there's still power to your phone, whether it's on or off. Now, when people are in these specific clandestine situations, which this is a realistic thing that happens, oftentimes electronics are just stashed away somewhere. Now, if I leave my thing in my cell phone in my car, somebody could still track where I am. And maybe they couldn't hear me, but they would know that, oh, my car is parked here, my phone is parked here, he's doing something in this area. And they'd be able to then start to try to figure out what I'm doing as a spy. So instead, you can put your phones in a special box, or it's referred to as a cage. Have you guys ever heard of a Faraday cage? So a Faraday cage is a box made of a particular type of metal. I assume it's lead, but I don't know that off the top of my head, that stops all radio signals in and out. It'll stop all radiation, so that there's no possibility that anybody would ever find that phone or hear anything from that phone because there's just no access to it. People do this with computers, cell phones and stuff when they're in these really important or confidential meetings. Now, turns out that Michael Faraday is a guy that was doing a ton of work with electromagnetism. And he discovered that magnets are kind of wonky, right? And anybody who's ever played with a magnet knows that they're kind of wonky because magnets attract even when they don't touch. That's called a what? A field force. Now, you do not have to draw this, but it's nice to see. Did you guys cover magnet stuff very hard in physical science? Okay, so if you've never seen it, I imagine that we've looked at that thing that I have in here somewhere. But assume we have a magnet, and every magnet has two poles, yeah? They're north and south. Now, as I get closer to a magnet, does it get stronger? If I have two magnets and I hold them this far apart, am I going to feel it as strong as if I hold them right here? It gets stronger attraction as we get nearer, right? That's the inverse square law. So as we're looking at it, what Faraday discovered, and you guys have seen the physical manifestation with this thing, we've all passed this around, right? Okay, what Faraday discovered was that electromagnetism travels in fields. And it turns out that they look essentially like this. They're really close together until you get further away, and it'd be coming out the other side. But the fields flow from north to south. This was Faraday's big discovery in 1831. So we had never known about electromagnetic fields until 1831 when Faraday was able to show this. Okay, this idea seems obviously very different than gravity because they are very different. They're completely different forces. However, once Faraday made this realization, the idea that fields exist within our universe, and like literally fields that exist out there, they can probably be applied to gravity too. So we have this new idea where gravity works as a field. So similar, and I'm going to use a shorthand, and I want you guys, before you write it, to let me know if you know what it is. Similar to EMAG. Any thoughts on what EMAG is? Electromagnetism. So if we need that here, it's gross, and it's a really long word. I would advocate let's write EMAG instead, but I'll write it this time. Similar to electromagnetism, gravity is a field. Now, whether or not this is a true statement just based on the way it's worded, depends on, what level we're looking at. But gravity does work as a field. So we have this idea, and it turns out that there's some pretty sweet and easy math that we can get out of this. My big warning about this value of G, what was it? Like, what was my warning to you guys about when you use this G? It's different on every planet, and in fact, it's different at every height. And this is what tells you how fast something accelerates. Now, one of the things I asked you guys to do on your project is to find the gravitational field strength. So let's knock this out. Here we go. The gravitational field strength. Every single thing in our universe creates a gravitational field. And it's dictated by a couple different things, but there's really only two major things that we need. The gravitational field strength we are going to represent with the lowercase g. Okay, immediately, this G does not typically have subscripts, but it varies. We always know that G up to now has been what? 9.8, right? Towards the center of our planet. We've worked under the assumption that we are on Earth. We will continue working under the assumption on Earth unless we're not. Does that make sense? Okay, if you want to use subscripts and stuff while you do it, I'm fine with that. But it turns out it's actually pretty easy to calculate. If you want the gravitational field strength of any object, first thing you need is G. Cool, or it is G rather. So we need the gravitational constant, which doesn't matter where you are. So here it is, capital G. Then only two other things. We need the mass of the single object that we're dealing with. How much gravity does it produce? We just need its mass. And then all we need is the radius of that object. So what I can see, and we've seen it and discussed it a little bit, once we get into Einstein, brief mention of black holes, but you take a really lot of mass and make it really, really small. When you divide by a smaller and smaller and smaller number, it gets bigger and bigger, right? Like, that's what happens. And I can see that black holes follow this rule as we're looking at it. Okay, can't stress this enough so much, I'm going to put a big warning right here. Warning. Warning. I want you to think of that like silly tone in your head every time. Warning. G equals 9.8. Where? Only on Earth. Now, for this, because we're talking about the strength of a field, I know that it's 9.8 meters per second squared, but when we're talking about strength of forces and gravities of force, we're going to go ahead and just commit to newtons per kilogram. This winds up being meters per second squared, but we have it. This 9.8 newtons per kilogram is only on the surface of Earth. Okay. Now, one of the things totally just, you're going to be the person that's aware of this. In calculus, you can deal with things changing constantly, right? So if I drop something from really, really high, realistically, the acceleration does change because the rate of change is like increasing or decreasing as we get closer to the planet, right? There is calculus needed to actually do the full calculations if we drop objects. because I can see there's a derivative just waiting to be worked out here. Okay, so looking at this, entirely up to you if you want this picture, but I think it's helpful. Let's say that here is a planet. I'm going to say it's P. Now, if I look around this planet, there's going to be a bunch of kind of random places, and I'm not picking these by any sort of like specific value. It almost looks like a picture of an atom. But check it out. I have 3 distinct orbits up here on the screen right now. So 3 places around this planet where maybe I'm looking at it. Hypothetically, if this were planet Earth and I were to connect, say, this line right from the surface, what would G be equal to? We'll say E for Earth. 9.8. And what's the label we're going to use for this? 9.8 newtons per kilogram. I think that was Sean. Thank you. Okay. Hypothetically, and we don't have any basis for the actual calculations here, what if I wanted it here? Let's guess a number. Now, we're not going to be perfect, but we're going to be able to tell right or wrong really easily. Mickey, if gravity is 9.8 newtons per kilogram on the surface of this planet, give me any number that you think is reasonable for out here. So, check it out. I like where your head's at. Did our radius get bigger or smaller? So the mass of the planet didn't change, right? So now, hypothetically, let's say I was dividing by 1 initially. Did the radius get bigger and now I'm dividing by like 2? Is this distance here larger than this distance here? So if this radius gets bigger, what happens to the overall number? Are you sure? Like if I take 10 over 1 and compare it to 10 over 2, this is much smaller. Do you agree with that? So when my radius gets bigger, this thing better be smaller. Now, how much smaller is where, like, this is total shot in the dark. Doesn't matter what your number is, as long as it is less than 9.8. Has to be. So any number less than 9.8, I'll take it. Cool. 7.8. Now, based on this answer, we didn't do any calculation. There is a height around our planet for which this would be the case. But what if I went out here? Now, I'm in the 3rd furthest orbit. What do you think, Toli? Give me any number that's reasonable for this gravity out here. 5.4. Love it. Now, all I'm checking, literally all I'm checking is the number getting smaller, right? Because gravity gets less strong. Okay. Will it ever get to 0, no matter how big I draw this? Not quite, right? Because as long as there's a distance, even if it's like crazy, crazy big, there's still a distance that you have to divide by, and you have something in the numerator. It's never quite 0. So I'm just going to take one more, and this is not to scale. Fern, give me one more number that seems like dumb, like too low maybe. 2.6. I like 0.26, but you can write whatever you want. Okay, it gets tiny, right? It can get infinitely small. Okay, this idea hopefully clarifies that something that we already kind of maybe saw yesterday. The International Space Station, or whatever it was orbiting up there, its acceleration was like 7 instead of 9. We were super far away. Okay, now for this next piece, I don't think we need to draw it. I'm just going to add it on here. If we wanted to add the gravity, and gravity is a vector, and I know that it causes centripetal force. If I were to look at it, gravity is pretty strong near the planet. So all of these might represent the gravity. And it's weird to think about because I can't draw 3-dimensional space. But I do think that all of those are roughly the same size, yeah? If I went out further, would gravity still be pulling? What would happen with my vectors, though? Would they be bigger or smaller as I get further away? Smaller, right? Because the magnitude of my force is decreasing. So we see this happening all the way everywhere around it. It's weird to think about, but everywhere, towards me, from every direction, no matter what, just like water pressure. Okay. Gravitational fields exist always towards the center, and they essentially go all the way out forever and ever and ever and ever. Now, what might make the influence of these vectors that I've drawn, this gravitational attraction, why doesn't everything in the universe pull to us then? Talk it out with your neighbors. The question is, like, if Earth pulls everything with gravity, why aren't we everything in the universe right here? Why haven't we pulled every other piece of matter that's ever existed and will exist to us? Talk it out. Get like 30 seconds. There's a quick answer, I think. Thoughts? If you answer the question. Yeah, not only just that, but there's like everything pulls on everything, right? So there's other stuff that's pulling other stuff harder or less hard than we are. Cool. It's a really big complex system. Cool. Now, as we look at it, we are sneaking into a field of math that's really complex, but we're just going to look at the very basics. Have you guys ever heard of chaos theory? Okay, so there's things in our universe that are like crazy hard to predict for us because there's so many moving pieces. Moving dynamic is the word that means moving. So if you're going to actually take a math class on something like chaos theory to try to predict the unpredictable, you would be taking a class maybe called chaos theory, but more likely dynamical systems, because they're systems where stuff changes. If you guys have ever heard of the three-body problem, that's like the intro into chaos theory stuff. If you've never heard of it, I would suggest you check it out. It's pretty cool. However, I want us to think about one little thing, and I'm going to give you guys a moment to talk it out with one another. I want to think, what if there's more than just two objects? What if one object is pulled by two masses? Now, there are a bunch of different ways that we could set this up. I'm going to set it up the nicest possible way. So let's say we have, hanging out here, a big mass here. And we're just going to say these are all the same material, so the size is relevant. One of them is more massive than the other. Let's say here's mass 1. And then all the way over here we have a smaller mass 2. And then somewhere in between is another smaller one that we're just going to do this little dot. And I'll say, look at that, mass 3. Cool. Now, as we look at this, what I want you to do, without having specific values, that's okay. I want you to draw the gravitational vectors, like show me the vectors that are acting on mass 3 and mass 2 and mass 1, and tell me which way do you think things are going to move in the end. So I'll give you a wrong example. Wrong example is if I say I think that this mass pushes things out like that, this one pulls that direction. Like, this is wrong, but I've drawn 3 vectors of equal size roughly. I don't think that's really what happens. I want you to draw me the vectors. I'm going to make it even a little bit easier. Show me the gravitational attraction that 3 gets pulled on by 1 and 2. We'll make that a nice first step. 2 vectors from mass 3. Just from our first object. Let's forget about everything else. Mass 3 doesn't get pulled toward mass 1. It does. Now, you tell me when to stop. There's not a right or a wrong answer. Stop there. Okay. I'm going to call this G1. And I'm going to say G1 on 3. Okay. Does mass 2 pull on mass 3? Similarly, right? Okay, so check it out. From here, you tell me when to stop. About there? Okay. So we will say that this is the gravitational pull from 2 on object 3. Now, who wins this fight? Mass 1, right? So I think, and I'm pretty confident in this, that what's going to happen is mass 3 is going to move towards mass 1, just based on this picture, right? Okay, now, in reality, this is all I need you to draw, just so we can see it. I lied, I'm going to put one more. I'm going to change color, and I think it's reasonable that with what we have here, what I see is there's going to be some sort of acceleration in that direction. The object is going to be pulled toward it because I have unbalanced forces acting on it. That's what acceleration means. Okay. However, if we wanted to go a step further, and this is just food for thought, is there this as well? That's gravitational attraction of 1 on 2. Now, what winds up happening, and this can be challenging to think about, but if you're watching this just on the video, you're not going to get to see this part. I think that this object is going to start moving first. Would you agree? This one is also going to pull to it, But notice the distance, because this one's closer and gets pulled harder, the distance between these starts to get bigger and bigger, and I start to get less pull, and all of a sudden this can be a really complex system to try to make sense of. Now, this is like the basic version of the three-body. Let's say that these things were all spinning and rotating like objects actually do in space. Do you think the math gets a little harder? Absolutely. I'm going to take a quick little 2-minute brain break. I'm going to show you my favorite chaos theory desk toy that I'm pretty sure I'm going to order myself. Baller. Now, last little thing, and I need like 5 more minutes. That's it. When we talk about mass, we have defined it over and over, at least, I mean, maybe. We use mass all the time. What's mass? All right, we'll do a quick recall. I'm going to walk around, get my steps in, take a drink of coffee. Talk it out. What is mass? Matter that does something specific, if that's the definition you're going to take.
It's like something with the gravity force of gravity.
Now, I'm going to just jot down a couple things that I've heard. We're going to have a small section about mass. I'm open to hearing what you guys had to say, though. Somebody want to volunteer before I just call randomly? What'd you say, Fern? Okay, so I'm just going to jot a few things down. You guys don't have to write yet. Okay, I'll go back to black when I'm writing. Okay, the matter. Now, if you talk about the matter in stuff, all you're going to say the matter that takes up space and has mass, right? Like that's what matter is. So something about the weight inside of it, kind of, right? Now, you related that to something else I heard. I was going to write it all, but I decided against it. Something about something to do with gravity, right? Now, if I weren't experiencing any gravity, like, for example, I'm in free fall around the planet, so it feels like I'm, like, not feeling gravity, right, on the space shuttle. Could you measure mass on the space shuttle still? Even though you're freely falling, you're in free fall. Like we saw in that video they talked about, if I hold an apple, if I drop it, it just hangs out in front of me. Could I get its mass still? How? Like, because clearly it still has it, yeah? Which means we need some way to talk about this where even in that moving situation where we're in free fall, there is still mass. It must still be able to be measured. But it's very different than just like weighing something on the planet, yeah? Fundamentally different because I can't do that. So it turns out, for our purposes, we have 2 ways that we can think about mass. So 2 kinds of mass that are really the same thing, we think. Pretty sure. I'm not pretty sure, but seemingly physicists are pretty sure. So I'm going to trust their judgment here. 2 kinds of mass that we deal with. We have what is known as inertial mass, which, just as a reminder, inertia is a tendency of an object to resist a change in its motion. So a car has a lot of inertia compared to this box, because I can just push that box right there. Can't push a car with that same force, right? The mass of it dictates how hard it is to push. So inertial mass, really easy to define. We're just going to say resistance. I'll say inertial mass, my bad. Resistance to, and there's a couple ways we can say this. You can just say force, or you can say delta V, because I'm resisting movement. Now, even in a freely falling body, if you imagine that I had a car also falling freely with me, so we're in like the largest space station ever, I can't set it on a scale and get a mass out of it. However, could I still try to push it? If we're both falling together, I could try to push it, right? And I'm probably not going to be able to. If I had next to the car an apple and I tried to push it, would I be able to push it? So clearly I can see that, hey, there is a difference in the mass that we're dealing with here. And this is the one that I think is more natural. Maybe. It depends. Inertial mass, as we're looking at it, we'll just define it. Super easy. M, inertia. Newton hooked us up. Turns out it's just the net force acting on an object over, what would Newton tell us this is over? F and M tied together in a single equation. Good thought. I think you're on the right track. Depends on what gravity you want to talk about. I like it. So acceleration due to gravity. This is how we think of stuff typically. Cool. This is a regular old mass that uses Newton's second law. Now, realistically, whether or not this is truly the one that we think of most of the time, I don't know. It depends on the person. I don't really think of how hard it is to push something in free fall, but we've used this to calculate out our mass before. Beyond that, we also get mass that is 100% due to gravity. Weird. So we have gravitational, and this should be capital. I don't know why it's not, but I'm too far into commit now. Gravitational mass. Now, instead of just seeing how hard is it to push something, this is how does an object interact with gravity, and specifically interactions with gravitational forces. I'm just going to say interaction with gravity. I'm fine with that. Okay. So Newton's first law comes out, or second law, says force is mass times acceleration. We can rearrange to get this idea of mass. Alternatively, using some rearranging of Newton's law of universal gravitation, we can get what's called gravitational mass. Last statement. Turns out by rearranging Newton's law of universal gravitation, if you take the radius of an object and multiply it by the force of gravity that that object experiences, and simply divide by the gravitational constant times mass of the object, you now get what's known as a gravitational mass. Okay, this is much more common. This is us putting something on a scale because we can see that it pushes the scale down because it creates a force due to gravity. Okay, not going to write this last part down. These look very different, I think. Seemingly, this is known as the equivalence principle. There's never been an observation made that says that this isn't true. These are, in fact, equal. They're just two different ways to think about the same concept. Seemingly true. Not confirmed true, but everybody just kind of accepts that it is true, at least at our level. Cool? All right. I'm good with that today. We're going to do Einstein tomorrow, which means you get 20 minutes of project research. Cool, cool, cool.